Somewhere between 80 and 90% of the mass in every single galaxy is completely invisible. These particles are streaming through the room you are sitting in right now. We are swimming in a dense, entirely unseen ocean. To understand how we know it's there, we have to look at a typical galaxy. Almost all the material we can actually see, the stars and luminous gas, is compressed tightly into the immensely bright central core. This chart plots the orbital velocity of stars against their distance from the galactic center. Newtonian physics dictates that because the core holds the bulk of the mass, stars at the far outer edges should move significantly slower than those near the center. But when we map the actual observed data across the universe, the line shoots up and flatlines. The outermost stars do not slow down. They are orbiting at such high velocities that the galaxy should immediately tear itself apart. The luminous material is misleading. Without an enormous, invisible mass generating enough gravity to hold everything together, our universe physically cannot exist. Physicists spent decades trying to explain away this extra gravity. They tried tweaking the math or searching for flaws in Einstein's relativity. Every attempt failed. The next assumption is that the missing mass is simply dim, normal matter, things that are just hard to spot with a telescope, like rogue space rocks or dead planets or hidden black holes. We can rule that out. Measurements taken from the very early universe tell us exactly how much normal matter was created during the Big Bang. There is not enough of it to account for these massive gravitational effects. We are forced to accept the reality that there is an undeniable hole in our understanding of reality, and known physics cannot fill the void. Even though we can't see the matter, we can precisely map its gravitational footprint. We know that every galaxy in the universe is surrounded by an immense ball of this invisible mass, called a halo. By observing how these structures behave, astronomers discovered that every dark matter halo shares an identical evolutionary shape, known as the NFW profile. They all form with a dense central core that slowly accumulates outward over time. To build a structure with this specific shape, the mystery matter must obey strict physical rules. First, it must be cold, meaning it moves slowly compared to the speed of light. Second, it must be collisionless. It ignores normal matter, streaming right through it, and it does not even interact with itself. Dark matter is not kinetic. It operates as a rigid, universally predictable architectural scaffolding that dictates exactly how the cosmos evolves. Looking for an invisible, untouchable, cold particle might seem like a wild guess by desperate physicists, but dark particles aren't a myth. We already know they exist, and we have measured them using our established models of particle physics. The neutrino is an undeniable, verified physical example of dark matter. It is a particle that has mass, yet completely ignores light. The limitation is its size. While it proves the concept, the neutrinos we know about are not heavy or abundant enough to account for the missing 27% of the universe's energy pie. The existence of the neutrino provides a physical proof of concept. It turns the search for an abstract astrophysical anomaly into a targeted hunt for a heavier, unmapped particle. That hunt is happening right now. Observatories and theorists around the world are looking for heavier theoretical candidates, like weakly interacting massive particles, or WIMPs, and ultralight axions. These detection methods require immense patience. Scientists build deep underground, ultra-cold cryogenic chambers filled with pure liquid xenon, waiting for years for a single microscopic heat flash or a faint burst of light from a dark matter collision. The dark matter anomaly provides a specific set of clues that point directly towards physics we haven't discovered yet. Finding this particle would provide a data point from the first few seconds of the Big Bang. Its mass and its behavior act as a record of the forces that shaped the early universe, specifically regarding an event called baryogenesis. In those first moments, matter and antimatter should have annihilated each other completely, leaving an empty universe. Because dark matter outweighs normal matter 5-to-1, its specific role in that early chaos likely explains why a tiny excess of matter survived to form stars and planets. Dark matter is the invisible foundation of the cosmos. We can map its shape and measure its weight, but we are still waiting for that first definitive signal to confirm what the house is actually built of.